Welcome back. Well, I'm now going to do, probably just a bunch of integration by parts problems. Well, as many as I can do in 10 minutes without confusing you. So let me just write the formula for integration by parts. And if you ever forget it, I mean, it doesn't hurt to memorize it, but if you ever forget it, you just literally have to just derive it from the product rule of differentiation. But it just says that if we have an integral of f of x times g prime of x, right? So if you see within the integral sign, you see one function and then you see the derivative of another function. And I think with practice, integration by parts is really a bit of an art. It's not kind of systematic. That's g prime of x. That equals f of x times g of x, right? This is how it's the product rule in reverse, minus the integral of the derivative of the first function, f prime of x, times the second function, right? And it's kind of easy to memorize because there's this symmetry to the formula, d of x. So let's see if we can apply this. And really, once you know that you should use integration by parts, I think you'll find that it's not that hard to do it. The hard part is to recognize when you should use integration by parts. From my point of view, it's kind of my last resort, or once you have a lot of practice, you might recognize, well, if there's an e to the x in it, or if there's a trig function in it, and I can't do the reverse chain rule or integration by substitution, then integration by parts is probably my best option, assuming I'm seeing this on an exam and not in real life. In real life, it might be an unsolvable integral, and you'd have to use a computer or some other technique. But if you're seeing it on an exam, you know it's a solvable integral, and if you can't solve it any other way, it's probably integration by parts. But let's just do some problems. Let's say I want to take the integral of x squared e to the x dx. So if I saw this out of the blue and I didn't know that this was a presentation on the integration by parts, I would first, clearly this isn't a polynomial, so I can't just do the simple polynomial antiderivative. Then I would try to see, well, is there the derivative of something that of one function, of a composite function here, so I can do the reverse chain rule. Let's see, the derivative of x here is 1, so no, I can't do anything here. So I use the chain rule. And the way I think about the chain rule is I want to simplify it, right? So when I go into this term right here, I have to pick up my f of x. I have to pick my f of x out of probably one of these two functions so that the f prime of x is simpler, right? And I need to pick my g prime of x, right? Either, I would guess that either x squared is going to be my g prime of x, or e to the x is going to be my g prime of x. And I want to pick that so that when I take the antiderivative of it, it's going to be simpler, or at least not more complicated. Well, I know that if I take the derivative of x squared, that simplifies it. And I also know that and once again, this is one of to me, a very mind-blowing idea, but the antiderivative of e to the x is e to the x. So it's probably a good idea to say that f of x is equal to, let me change the colors. It's probably a good idea to make f of x is equal to x squared, because later I'm going to take the derivative of it, and the derivative of it simplifies it. And it's probably a good idea to make g prime of x e to the x, because later I'm going to take the antiderivative of it, and the antiderivative of e to the x is e to the x. It's not going to become any more complicated. So if we assume, if what I'm doing is right, then what did we say? Well, here we just multiply the two, the real functions, right? So when I say the real functions, I mean kind of not the derivatives of either one of them. So f of x, we're saying f of x is x squared. I'm trying to stay color consistent. X squared. And we said g of x. Now don't get confused. We're saying g prime of x. Let me write it in a little corner down here. We're saying that g prime of x is equal to e to the x. And of course, if g prime of x is equal to ex, then g of x is also equal to e to the x, right? So g of x, I don't want you to think that I'm somehow putting g prime of x here. I've taken the antiderivative. It just happens to be the same function, is e to the x. And then from that, we subtract the integral. We take the derivative of x squared, so you get 2x, right? And then times the antiderivative of g prime of x. Well, g prime of x is e to the x. You take the antiderivative. Well, it's still e to the x, right? Actually, I should probably stay. Let me keep the colors kind of consistent so you know what I'm hopefully doing. E to the x. And the example using e to the x might be a little complicated because it's hard to tell whether I've taken the derivative or not. And you can kind of keep reverting back to the top formula if you get confused. Let me pick this color. dx. So it looks like I've simplified it a little bit. This integral looks easier to solve than this integral. But once again, when I look at this, I'm like, well, how do I solve this? I can't use the integration by substitution, right? Because there's not like I have an embedded function and then I have the derivative of it sitting right next to it. So maybe I need to do integration by parts again. So let's do that. So let's say, let me do it separately. Well, let's assume, I think you're getting a little bit of the hang of it, along the same vein that this is f of x, that this is f of x, and that this is g prime of x now, right? We're doing integration by parts within integration by parts. So if that is the case, that this integral is going to equal, right, because we have the minus sign out front, right, this minus sign out front. This integral is going to equal f of x times g of x, or f of x is just 2x. Our g of x, this is g prime of x now, right? Remember, we're kind of doing a new problem within the original big problem. So this is g prime of x, but g of x is still just e of x, right? I took the antiderivative of it. And then that's minus the integral of the derivative of the first function, right? F prime of x. So that's just 2. And then the antiderivative of the second function. Well, that's easy. The antiderivative of e to the x is just e to the x. Interesting. Now I think you see where we're going. This is actually, let me write the whole thing, right? Because this is x squared e to the x, just so we don't lose track of our original problem. Interesting. Now I think we have an integral that is pretty straightforward to solve, right? Oh, no, don't want to forget my dx's. What's the integral of, we could take this 2 out of this, right? And I think it becomes pretty obvious. What's the integral of e to the x? This is scratch out. This says dx. Just so, I know it's a little messy. I don't like this color. Magenta. Well, the integral of e to the x is the antiderivative of e to the x is e to the x, right? So let's write that. So I'm going to rewrite everything we've done. So there's x squared e to the x minus 2x e to the x, right? And then this minus, you distribute it, so it becomes a plus. So then it's plus 2, right? I just took the minus, I multiplied it times this minus, so I got a plus 2. And then the antiderivative of e to the x is just e to the x. And then, of course, we should never forget the plus c. Pretty fancy, no? Let's see. We figured out the antiderivative, or the indefinite integral of x squared e to the x is this big fancy thing. I bet you before listening to this video, you would never imagine that you could tackle integration like this. And you know, you could actually try x to the n times e to the x. You could try x to the 10th times e to the x, and it actually turns out you'll just have to do this many times. But every time you do integration by parts, that the exponent on the x term just becomes smaller and smaller and smaller until you get to something that's really easy to integrate, and then you can do it, and you'll have kind of this big long expression. It might be tedious, it might be hairy, but at least you have a toolkit, or you have something in your toolkit that you can tackle integral problems like this. I'll probably do one more video on integration by parts, just because I think this is one of the harder concepts to really grasp and feel comfortable with. And then I'll try to do a bunch of examples, maybe not soon, but in the next couple of weeks, on just a lot of integration, and I'm going to mix it up so that hopefully you can get a sense of how I try to figure out which of my integration tools I should use for a certain problem when I see the problem. See you in the next presentation.